In this video, we'll discuss another method for estimating causal effects from data, called inverse probability weighting. We've talked about regression, which conditions on variables to block non-causal paths. This is one way to remove the undesired, non-causal parts of observed associations between treatment and outcome. Another way is to effectively alter non-causal paths so that they no longer carry unwanted associations. For example, what if we were able to delete the Z to A arrow in this graph? If we could do this, then this non-causal path would no longer exist, marginal exchangeability would hold, and we could directly compare the observed outcomes in the treated and untreated to estimate the average causal effect. This idea is called inverse probability weighting. Let's develop this method using this ZAY causal graph to frame ideas. The data we collect on Z, A, and Y can be organized in a tree diagram as shown here. For simplicity, we'll work under this situation where all variables are binary, but everything we discuss can be generalized to 3 or more categories, as well as quantitative variables. The reason that we show Z, then A, then Y from left to right is to indicate the flow of time, as indicated by the arrows on the diag. Let's say that there are 100 people in our study, 60 of whom have Z equals 1, and 40 of whom have Z equals 0. Within both of these groups, there are some who receive treatment and some who don't. Finally, within each of these 4 groups, people experience both the Y equals 1 and Y equals 0 outcomes, success and failure. If this causal graph is an accurate representation of the world, then we have conditional exchangeability given Z. This means that within Z equals 1 and within Z equals 0, the observed outcome distributions accurately represent the missing potential outcomes. In other words, the 90% success rate for the treated within Z equals 1 accurately represents the treated potential outcome distribution in this Z equals 1 subgroup. This 90% should accurately reflect the missing treated potential outcomes among the untreated. Similarly, the 40% success rate for the untreated accurately represents the YA equals 0 potential outcome distribution in this Z equals 1 subgroup. This 40% should accurately represent the missing, untreated potential outcome distribution among the treated. This idea of using exchangeability to fill in the missing potential outcomes is effectively simulating interventions where everyone in our sample receives treatment or does not receive treatment. Let's step through this process. Let's first simulate the situation where all individuals in our sample receive treatment. In other words, we're obtaining the YA equals 1 potential outcome for everyone. This means that in the Z equals 1 subset, all 60 people will be receiving treatment, removing the 30 untreated to be treated. And within the Z equals 0 subset, all 40 people will be receiving treatment, removing the 10 untreated to be treated. Because among the Z equals 1 treated, there was a 90% success rate, that 90% should still hold for the additional 30 that have been added. So among these 60 treated, 54 should have a success outcome and 10% should have a failure. Among the Z equals 0 treated, there's a 70% success rate. That should still hold for the 10 extra individuals. So in these 40 treated, 28 should have a success outcome and 12 should have a failure. So we've directly applied the concept of conditional exchangeability to simulate what would happen to everyone in our sample had they been treated. We've filled in the missing YA equals 1 potential outcomes. We'll use analogous reasoning to fill in all of the missing YA equals 0 potential outcomes. But first, let's make a key observation that illustrates why this method is called inverse probability weighting. In the Z equals 1 branch, each of the original 30 treated individuals counts twice in simulating the 60 Z equals 1 individuals being treated. Half of the Z equals 1 people were treated, and we're scaling up the same outcome distribution observed in this group. In the Z equals 0 branch, each of the original 30 treated counts 4/3 times to scale up the number of treated to be 40. So the 2 and the 4/3 are called weights. Within Z equals 1, the 30 treated have a weight of 2, and within Z equals 0, the 30 treated have a weight of 4/3. These weights actually have a special relationship to the probability of receiving treatment. The probability of receiving treatment within Z equals 1 is 30 out of 60, or 1/2. And the weight in this branch is the inverse of this probability. The probability of receiving treatment in the Z equals 0 branch is 30 out of 40, or 3/4. and the weight in this branch is the inverse of this probability. For this reason, this method of reweighting observed outcomes to simulate interventions is called inverse probability weighting, or IPW. It also goes by the slightly longer name inverse probability of treatment weighting, or IPTW. We can estimate the average potential outcome using the reweighted outcomes. The average of the 54 ones, 6 zeros, 28 ones, and 12 zeros in this set of reweighted outcomes is 82%, which can be interpreted as the probability of a successful outcome if everyone were forced to receive treatment. So note that this can also be expressed as a weighted average of the original outcomes of the 60 treated individuals. Now that we've seen how conditional exchangeability can be used to simulate all study subjects being treated, let's repeat the process for simulating everyone being untreated. We start with the same tree diagram showing how our data fall into different levels of Z, A, and Y, but this time we'll have all 60 Z equals 1 people be untreated, and we'll have all 40 Z equals 0 people be untreated. Among the Z equals 1 untreated, there's a 40% success rate. So when we maintain this rate for all 60 of the Z equals 1 people being untreated, then 24 will have a success and 36 will have a failure. Note that in this scaling up, each untreated person in the Z equals 1 branch counts twice, and this weight of 2 is equal to the inverse of the probability of being untreated in the Z equals 1 branch. Among the Z equals 0 untreated, there's a 20% success rate. So when we maintain this rate for all 40 of the Z equals 0 people being untreated, there will be 8 success outcomes and 32 failures. Just as before, note that with this upscaling, each untreated person in the Z equals 0 branch counts 4 times, and this weight of 4 is equal to the inverse of the probability of being untreated in this Z equals 0 branch. Just like when we simulated all being treated, we can average the reweighted outcomes to estimate the average outcome. This estimate of 32% can be interpreted as the probability of a successful outcome if everyone were forced to not receive treatment. Because we have estimated the average potential outcomes under treatment and under no treatment, we can estimate the average causal effect as the difference. This difference of 50% can be interpreted as if we treated everyone as opposed to treating no one, the probability of a successful outcome would be 50% higher. So let's return to the idea that we mentioned at the start of the video about the 2 ways to deal with non-causal paths and causal graphs. We mentioned that inverse probability, IP, weighting was a way to remove arrows from non-causal paths. Have we actually done that? If the arrow from Z to A were removed by this process, then Z and A would be independent after this reweighting. This is in fact true, and we can look at the total weighted population to see. The total weighted population is this collection where all 100 of our study participants exist twice. Once for each treatment they received in our simulations of treat everyone and treat no one. Because all study units exist twice, this total weighted population is also called a pseudopopulation, and it's a population of effectively 200 people. In this pseudopopulation, Z and A are independent. Why? Because each of the original 100 people both receive and don't receive treatment regardless of their value of Z. The marginal probability of both A equals 0 and A equals 1 in the pseudopopulation is 50%, and all conditional probabilities of A given Z are also 50%. Verify for yourselves the conditional probabilities that are shown here, all of which are in the pseudopopulation. So there really is no arrow from Z to A in the pseudopopulation. This is in contrast to the original data where the marginal and conditional probabilities differ. Within Z equals 0, treatment is more likely than in Z equals 1. So the Z to A arrow is still as present. And the A, Z, Y non-causal path is still carrying unwanted associations. But our use of inverse probability weighting rectified this by removing the Z to A arrow, as we just saw. In summary, inverse probability weighting provides another way to deal with non-causal paths in causal graphs by essentially removing arrows. To obtain appropriate weights, we need to know the probability of receiving the different treatment values conditional on the variables needed to achieve conditional exchangeability. Essentially, IPW simulates interventions where everyone receives and doesn't receive treatment by reproportioning, reweighting observed outcomes to create a setting where all study subjects receive each treatment value. In doing this, we have a completed set of potential outcomes that we can use to estimate average causal effects.